Hi. Today I want to talk about what is right now maybe my favorite problem in math, and it's all related to this sum s sub 2 of n, which is just the sum as k ranges from 1 to n of k squared, or in expanded form it becomes 1 squared plus 2 squared plus 3 squared, and so on all the way up to n squared. Now, for small values of n, this sum is really easy to compute. For instance, s sub 2 of 1 is just 1, s sub 2 of 2 is equal to 1 plus 4 equals 5, s sub 2 of 3 is 1 plus 4 plus 9, which is 14, and so on. But what happens when n gets larger? For instance, say that n is 100 or 1000 or even a million. Can we compute this sum by hand then? Of course, using the definition, this would be an impossible task. There are just too many terms and it would take too long to just write it down. But can we find maybe some easy to use formula to compute this number? Now, initially, I'll ask you to try and solve this problem completely on your own and see whether you can come up with any ideas that seem even remotely useful in this scenario. And it may just be that you're not really getting anywhere, and that's completely fine. In fact, for most people watching, that's what I'm expecting to happen. And it's sort of what I'm going to presuppose going forward in this video. But for now, just pause the video, spend maybe not more than 5 to 10 minutes at this stage, and try to solve the problem as best as you can on your own. So, have you tried to solve the problem and completely failed? Wonderful. Let's now talk about what we do in these situations when we don't really know what the next step is. Usually, when we get stuck on a difficult problem, it tends to be a good idea to sort of take a step back and consider some problems that are related or similar in spirit to the one we're trying to solve, but different in some major way. And the reason for this is that we want to sort of obtain some additional intuition about the problems we're dealing with, and maybe even get some ideas of what a good guess for the solution might be. And if that fails, we just want fresh ideas that we may not have thought of if we just focused on our main problem. And usually what we do is we try to look at the problem we have and see whether there is some aspect of it that we can simplify. Now, our problem is to find a good way to compute s sub 2 of n, where this is just a sum of squares. But how can we simplify or modify this problem so that it's related in spirit, but maybe different enough for us to sort of think in new directions? Well, the most straightforward thing is to replace the number 2 everywhere here with the number p. So here we have the number 2, and we can replace it with any number p we would like. And a very natural assumption would be that if we take p to be a smaller value than 2, then the problem is going to get a bit simplified, because then the expression k to the pth power would be simplified. So for instance, if we pick p equals to 0 or p equals to 1, then at least the individual terms in the sum will be easier to deal with than in the original problem. So let's see whether we can solve this problem for p equals 0 or 1. Well, for p equals 0, the problem is actually quite easy to solve. S sub 0 of n is just equal to the sum as k ranges from 1 to n of k to the 0th power. But k to the 0th power will just be equal to 1 no matter what k is. So this sum, when we write it out in expanded form, just becomes n copies of the number 1 added together. And that's just equal to n. So this problem is, a bit too easy to give us any concrete ideas for s sub 2 of n, but it does show us that s sub p of n can be computed sometimes, and this may give us some hope that the problem of computing s sub 2 of n may actually be solvable. So let's now consider s sub 1 of n instead. Now this sum is a lot more interesting, so it becomes the sum as k ranges from 1 to n of k to the 1th power, but k to the 1st power or 1th power is just equal to k. So this sum, when we expand it, just becomes 1 plus 2 plus 3 plus 4 and so on all the way up to n. Now, this does indeed look a bit easier than trying to find a way to compute s sub 2 of n, but this problem is not as easy as trying to compute s sub 0 of n. This is not at all trivial to solve. But it is possible to solve, and in the next couple of slides I'm going to showcase two different methods of solving this problem and deriving a formula for s sub 1 of n that applies for any number n. The first method I'm going to show has to do with geometry. So numbers of the form s sub 1 of n are often called triangular numbers, as they can be visualized by using triangles. So for instance, if we take the number s sub 1 of 4 here, we can visualize it as a ragged triangle in the image here below using Lego bricks. So first we have the term 1, then we have the next stack is the term 2, then the term 3, and then the term 4 finally. And we get that this shape here represents the sum s sub 1 of 4. Now, what does this geometric interpretation of s sub 1 of n actually do for us? Well, it turns our original problem with the sum into the problem of determining the area of this shape here. And this is a really big deal because we can compute this area in different ways. We can get inspiration from the fact that we know formulas for the areas of triangles, but more concretely, we can actually compute this area directly. And we do that in sort of a very elegant manner by copying this sum and flipping it upside down. And what does this give us? Well, it gives us the following shape. So first, here in the yellow, we have the original sum s sub 1 of 4, and then we add another copy of this number and turn it upside down, so to speak. So we get this red triangle, which is just the yellow triangle, but upside down. And when we combine these two shapes, we get a rectangle, which has width 4 plus 1 and height equals to 4, if we count in the number of Lego bricks. Now, the area of the rectangle is really easy to compute. It's just 4 plus 1 times 4. And since this area is just twice the area of the original triangle, we get that 2 times s sub 1 of 4 has to be this number, 4 plus 1 times 4. So from this, we just divide by 2 everywhere, and we get that s sub 1 of 4 is 4 plus 1 times 4 divided by 2, which is just equal to 10. And it's easy to check by hand that s sub 1 of 4 is indeed equal to 10. Now, this reasoning can be generalized to any natural number n, and it leads us to the following formula where we just replace the number 4 here with the number n everywhere. So we replace 4 with n, we replace 4 with n. And we end up with the formula s sub 1 of n is equal to n plus 1 times n divided by 2. And this formula, of course, works for any number n, and it gives us a very quick way to calculate s sub 1 of n, even for large values of n. So now, one might expect that we are going to progress to a different problem, but I'm actually really interested in staying on this problem for a bit longer and try to solve it using a different method. And that different method will have to do with how sums actually work at their core. And the one thing we really want to be able to use here is that any sum of finitely many terms can be computed by taking the terms in any order we would like, and we can also partition them in different ways. We can split up the sum in different ways. And of course, this is true for s sub 1 of n as well. So by definition, we have that s sub 1 of n is just equal to this sum, which is 1 plus 2 plus 3 plus 4 and so on, all the way up to n. But we might just as well write the sum backwards without any sort of consequence, like s sub 1 of n is just n plus n minus 1 plus n minus 2 and so on, all the way down to 1. Now, if you've seen how to solve this problem before, you might expect what I'm going to do next, but you will be wrong because I'm not at all going to do that. I'm going to do something that I think is far more interesting. And that has to do with the fact that if we look at this above expression here for s sub 1 of n, we saw that we actually had a way of expressing that using sum notation. But how do we express this thing here, this sum, using sum notation? Well, it will become the following thing here. S sub 1 of n, which is equal to this sum, is equal to the sum as k ranges from 1 to n of n plus 1 minus k. So what happens here really? Well, as we see here, the things being summed will decrease by 1 as k increases by 1. That's why we have minus k instead of plus some k. And why do we have the term n plus 1 in the front? Well, it has to do with the fact that we want the first term in this summation to be n. So when k equals 1, what happens here? We get n plus 1 minus 1. So then we get n. Okay, perfect. And when k equals n, then we want this to be equal to 1. So n plus 1 minus n is equal to 1. Okay, perfect. And every term decreases by 1 if k increases by 1. Okay, perfect. This is actually the way to write s of 1 of n backwards using sum notation. But what's the big deal here? Well, now we can actually start computing this sum using some fundamental properties of sums. So here we have s of 1 of n is equal to this expression using sum notation, but we can just split this sum up into two separate sums as follows. So now we have that the sum, as k ranges from 1 to n of n plus 1 minus k, is just the sum as k ranges from 1 to n of n plus 1 minus the sum as k ranges from 1 to n of k. But both of these sums that we have split up our original sum into are easy to rewrite. So the first sum here is just equal to n plus 1 times n, because n plus 1, which we try to sum, is just constant here. So we just got n copies of that number, and the sum of these is just n plus 1 times n. And this guy over here, well, it's just by definition equal to s of 1 of n. And from this now, we can take the right-hand side and move this term s of 1 of n over to the left-hand side. And what do we get? Well, we get that 2s of 1 of n is equal to n plus 1 times n, which gives us the formula from before. Before moving on, let's summarize quickly what we have accomplished so far. So we derived formulas for s of 0 of n, which is just equal to n, and s of 1 of n, which is n plus 1 times n over 2, or if we expand it becomes n squared plus n divided by 2. Now, s of 0 of n, that wasn't very difficult to deal with, but s of 1 of n was quite interesting to work out. And we used two different methods of deriving the formula for s of 1 of n. One was more geometric in nature, and the other one was more reliant on some fundamental properties of sums and how we could rearrange and partition things in a different way to get more information about the sum. But both of these have something in common, and that is that they gain information about s of 1 of n by viewing it from a different angle. With all this in mind, let's now return to the main problem of this video, which is to compute s of 2 of n by hand for large values of n. At this point, spend as much time as you'd like before proceeding and see whether you can use any of the ideas I've showcased so far to gain inspiration for solving the main problem of this video. From this point on, I will start talking about how we actually go about solving this problem. And the first thing I want to do is to talk about how we can interpret s of 2 of n geometrically. So for s of 1 of n, we got to the notion of triangular numbers, and the corresponding notion for s of 2 of n will be square-pyramidal numbers. And that is because we can represent these numbers by pyramids with a square base in the following manner. So in the picture to the right here, I have a representation of s of 2 of 4 with a pyramid with 4 layers. So the green block is just 1 squared, then the red blocks make up 2 squared, the yellow blocks make up 3 squared, and then finally the blue blocks make up 4 squared, or at least that's what they represent. But now comes the question, okay, can we actually use this visualization in some way to solve our problem? The answer to this question is yes, but we have to be a bit more clever than we were in the case for triangular numbers. And what we have to do is we need to combine this geometric perspective with some ideas we had from the second method of finding a formula for s of 1 of n. We need to use the visualization not just to compute some volume, but rather to use it in order to create alternative ways of writing down our sum. So I thought about how to best explain how we use this shape here in order to gain insights in how to view s of 2 of n in general. And let's now talk a bit about this shape and what it actually does. Well, it showcases that s of 2 of 4 can be thought of as this pyramid because we have 1 squared plus 2 squared plus 3 squared plus 4 squared, where each layer in the pyramid becomes one of the terms in the expression. But the fact of the matter is that any other way of constructing this pyramid will give us an alternative way of characterizing the sum s of 2 of 4. So let us now think about different ways of building this pyramidal shape. And the first way I want to talk about is to not think in terms of these horizontal layers like we have here, but rather in terms of vertical stacks. So first we can place a stack of height 4, and then around this stack we place 3 stacks of height 3. And then around these stacks we place 5 stacks of height 2. And then finally, around these 5 stacks, we place 7 stacks of height 1, which gives us an alternative way of viewing our pyramid, which in turn gives us an alternative way of viewing the sum that we're after. A second alternative way of viewing this pyramid, or how we build it, is to first take 4 copies of the same shape. Now, all these 4 copies are really the same thing. They are just s sub 1 of 4, which is the 4th triangular number. So we take 4 copies of that one, and then instead of adding successively to build our shape, we remove things from this shape here in order to create what we're after. So from this first red part, we need to remove the top layer, which is just 1. Then from the second yellow here, we need to remove the second triangular number. And then finally, from the blue part here, we need to remove the third triangular number. And by doing this construction, we see that we get, once again, the same pyramidal shape as before. Let's talk about what we just saw and how the observations we made for s sub 2 of 4 can be generalized. Originally, we had that s sub 2 of 4 is just 1 squared plus 2 squared plus 3 squared plus 4 squared, and using the visualization, we organized each term as a horizontal layer in a pyramid. But this pyramid shape can be built in many different ways, and in the first alternative view of s sub 2 of 4, we built the pyramid using vertical stacks instead of horizontal layers. Then we got that s sub 2 of 4 is 4 times 1 plus 3 times 3 plus 2 times 5 plus 1 times 7. So let's take that again and talk about what these numbers represent. So first, in green, we had 1 stack of height 4. Then in red, we had 3 stacks of height 3. Then in yellow, we got 5 stacks of height 2. And then finally, in blue, we got 7 stacks of height 1. Apart from the first alternative view of s sub 2 of 4, we also built the pyramid using the second alternative method, where we instead began by placing 4 copies of s sub 1 of 4, after which we removed first s sub 1 of 1 from the red part, then s sub 1 of 2 from the yellow part, and then finally s sub 1 of 3 from the blue part. This can be written in the following way using sum notation, where this part right here denotes all the terms that we had to remove from the original 4 copies of s sub 1 of 4 to create s sub 2 of 4. Both of these alternative characterizations of s sub 2 of 4 can be generalized to give us alternative ways of writing s sub 2 of n, and this is what we get. First, we get that originally s sub 2 of n is just the sum of squares that we saw from before, but in the first alternative something interesting happens. S sub 2 of n then becomes the sum, as k ranges from 1 to n, of n plus 1 minus k, which is a factor I will mark here in blue, times 2k minus 1, which is a factor I will mark in green. Now, how do we arrive at this way of writing s sub 2 of n from our previous slide? Well, let's look what happens. First, let's go back one slide and mark our factors in blue and green here as well. So first we have this number here, which is stack height. We have first 4, then we have 3, then we have 2, then we have 1. And then we take the green factors, which will become the number of stacks with said height. So we get like this. And notice what happens here. First we have the blue factors, which begin at 4, and then as you can see here, they decrease by 1 at each step. And then we have the green factors, and from this we see that they begin at 1, and then they increase by 2 for every step in the summation. So let's now look at the generalization of this behavior. We see that the first factor here, marked in blue, because of the minus k term in it, we see that it decreases by 1 if k increases by 1. And in the green factor, we see that if k increases by 1, then this factor will increase by 2 because we have 2k instead of just 1k. And if we just check here the initial term, we see that initially the blue factor will be n plus 1 minus 1, which is n. Well, that's a good sign. And if we look at the green factor, we see that initially that will be 2 times 1 minus 1, which is equal to 1. Now this is a perfect generalization of what we just saw, but it is something that you need to sort of work through before you fully understand what's going on. Now let us turn to the second way of writing down our sum here. So we had s sub 2 of 4 is equal to 4 times s sub 1 of 4 minus the sum as k ranges from 1 to 3 of s sub 1 of k. Now this is a lot more straightforward to generalize. As we can see here, s sub 2 of n can be written as n times s sub 1 of n minus the sum as k ranges from 1 to n minus 1 of s sub 1 of k. And this is almost perfect, but there are a few details here we want to note. First, we have this upper limit for the index k in the summation here needs to be n minus 1 instead of n. And if we look at the previous slide, we see that this has a 3 instead of the number 4 here. So here we have the number 4, but in the green part here we have number 3 instead. And if we look at the number 4 here, it should be replaced by n in the generalized formula everywhere. And behold, it is indeed replaced by n everywhere. And this is very straightforward, but it is something that you need to be able to write down using some notation to actually be able to use effectively. Now, next, I will begin showing you exactly how we can solve the problem of finding a formula for s sub 2 of n using these alternative characterizations. So if you still want to solve the problem on your own, I recommend that you pause the video and try to solve it for as long as you'd like. Then I will go on and explain in detail how we can use these alternatives to solve the problem. Now I will explain exactly how we solve the problem by using the second characterization of s sub 2 of n. So first, we take our expression and we expand the product and see what we get. And we end up with the following expression here within the brackets. So let's talk a bit about how we did this expansion so that there are no embers of confusion left afterwards. First, let's look at this term. Now this one is pretty easy. We just take minus k times 2k, no problem at all. And this is the only second degree term we get in our expression. Next, we have this big pile here, and that's something that we need to be careful with when we expand. So first off, how did we get 2 times n plus 1? Well, we take n here plus 1 from this factor, and then we take 2k from the other factor. And that's how we get 2 times n plus 1 times k. And now we can also have this way of getting something times k. We take minus k times minus 1. And that's why we have this term plus 1 within these parentheses as well. And then finally we have this final term minus n plus 1 in the expression, and that's just taking n plus 1 times minus 1. And that covers all the multiplications that we can make in this product. So let's split these up into separate sums. This leads us to the following expression. So minus 2 of the sum as k ranges from 1 to n of k squared plus 2n plus 3 times the sum as k ranges from 1 to n of k, then minus n plus 1 times the sum as k ranges from 1 to n of 1 simply. So we get that this first part here is just this minus 2 that we get from here. The second part here is just this expression here when we simplify it. And then finally we have that this final expression here is just something we get down here again. But all of these expressions can be written using our notation s sub p of n from before. We get that this expression is just minus 2 times s sub 2 of n plus 2n plus 3 times s sub 1 of n, and then finally minus n plus 1 times s sub 0 of n. But two of these, s sub 1 of n and s sub 0 of n, we already know what they are. We can write them using our formulas, and we get the following expression. Now, we can work directly from this, but what I like to do when I get these kinds of expressions is that I want to simplify them and clean them up a bit before moving on. And here I see a perfect opportunity to do so. For instance, here I see that we have n plus 1 times n, and then we have n plus 1 times n here as well. So when I break that out, I get the following expression here. I get that this is equal to minus 2 times s sub 2 of n plus n plus 1 half times n plus 1 times n. So basically, how do we get n plus 1 half here? Well, we take 2n minus 3 divided by 2 minus 1. And that's what this simplifies into. But here we see that we have more than just this expression here. We also have this part in the front as well. And now we can start manipulating this expression in order to sort of isolate s sub 2 of n. So we get the following, and then when we take this term and move it over to the left-hand side, we get the following expression. So we get that 3 s sub 2 of n is equal to n plus 1 half times n plus 1 times n. And now all we have to do is divide it by 3, and we get that s sub 2 of n is equal to n plus 1 half times n plus 1 times n, all divided by 3. And now we can of course expand this product as well, and we get the following formula, that s sub 2 of n is equal to 2n to the third power plus 3n to the second power plus n, all divided by 6. Now we've actually solved our problem, but I do want to go back to the second alternative way of viewing things. Because, you know, these alternative ways of viewing s sub 2 of n and solving the problem and finding a formula for s sub 2 of n, they are not that common actually. They're not at all the most common method of doing it. And I think that if you want to solve it using the second alternative, it will be hard for you to find an explanation of how it actually works outside of this video. So let us now focus on how we solve this problem using the second alternative way of viewing s sub 2 of n. So we had, using this alternative, that s sub 2 of n is equal to n times s sub 1 of n minus the sum as k ranges from 1 to not n but n minus 1 up here of s sub 1 of k. Now what I would like to do is to take this upper index in the summation and sort of turn it from n minus 1 into n to simplify things for me later on. And I do this by simply adding and subtracting a copy of s sub 1 of n, and I get the following, that I add a copy of s sub 1 of n to this guy here, to the first term, which gives me not n times s sub 1 of n, but rather n plus 1 times s sub 1 of n. And the effect it has on the other expression is, instead of having a sum ranging from k equals 1 to n minus 1, I get it to range from k equals 1 to n. So that's what I do. I rewrite the expression a tiny bit so that I get n in the upper limit for the index rather than n minus 1. And now we have the really fun situation where I know what s sub 1 of k is. I can rewrite this using my formula from before, and I get that this expression is equal to n plus 1 times s sub 1 of n minus the sum as k ranges from 1 to n of k squared plus k divided by 2. And now I do the same as I did for the previous alternative. I split this one up into two separate sums as follows. So I get that our expression is equal to n plus 1 times s sub 1 of n minus 1 half times the sum as k ranges from 1 to n of k squared minus 1 half times the sum as k ranges from 1 to n of k. But like I did for alternative 1, I can rewrite these sums using our notation from before, and I get that this guy is just equal to s sub 2 of n, and this guy is equal to s sub 1 of n. Nothing strange at all. And now I can also clean up a bit, and I see I have a factor s sub 1 of n here, I have the factor s sub 1 of n here. I can bring these together and rewrite this expression as the following. So instead of having n plus 1 times s sub 1 of n minus 1/2 of s sub 1 of n, I can write this as n plus 1/2 times s sub 1 of n. And I clean up the expression a tiny bit before moving on. So, continuing from the last slide, we had that s sub 2 of n is equal to n plus 1/2 times s sub 1 of n minus 1/2 times s sub 2 of n. And if I take this term here and move it over to the left-hand side, I get the following, that 3 over 2 times s sub 2 of n is equal to n plus 1/2 times s sub 1 of n. And if I divide by 3 over 2, I get that s sub 2 of n is equal to 2 times n plus 1/2 times s sub 1 of n all over 3. And this is indeed the same expression as I had before, because I have the formula for s sub 1 of n, and I can rewrite that as n plus 1 over n divided by 2. And then we see at the end of the day, we get the exact same expression for s sub 2 of n that we had before. With all this, we have now computed s sub p of n for p equals 0, 1, and 2, and I've written down all these formulas below in some alternative ways. But what happens after this? Where do we go from here? Well, let's ask some questions. First off, let's ask whether we can find a formula for s sub p of n for any natural number p. What we have already suggests this might be the case, but can we really be certain that all we have done so far can be generalized to any number p? Before moving forward, let's organize what we have into a table so that possible patterns emerge more clearly. So we have s sub p of n for p equals 0, 1, and 2, and when p was 0, then s sub p of n was just a first degree polynomial, and the lead coefficient, which is the coefficient in front of the term with the highest degree, is just equal to 1. Now, when p was equal to 1, we got a second degree polynomial, and the lead coefficient is now not 1, but rather 1/2. As you can see here, we have 1/2 in front of n squared. And then, when we look at p equals 2, we see that the degree is equal to 3, and the lead coefficient is now 1/3, which is this one in front of n cubed. And all this seems to suggest a pattern that we should be on the lookout for in the future. Namely that s sub p of n is a polynomial of degree p plus 1, and lead coefficient being 1 over p plus 1. But if we expand this table, maybe we can find even more things that we can look out for when we try to find s sub p of n for higher values of p. Now, at this point, of course I could just sort of go on and tell you all about this problem and how to solve it for different values of p. But I think that would be both tedious and kind of pointless, because at this point, I think that if you're interested in solving this problem for other values of p, you can actually try to do it on your own, and that would be so much more rewarding, in my opinion. Now, to get you started on this sort of exploration of the problem, I'd suggest that you look into some of these points that I'm listing below. So first off, try to see whether you can find the formula for s sub 3 of n with any method you'd like, i.e., try to see whether you can compute the sum of cubes quickly. Now, there is something very interesting with this formula in particular and how it relates to s sub 1 of n. But what is that exactly? And secondly, and thirdly, I'd like you to see whether you can find a way to show that these patterns that we saw in the previous slide actually do occur for all values of p, that they actually do continue. For instance, that s sub p of n is actually a polynomial of degree p plus 1. How can we show that? And thirdly, how can we prove that the leading coefficient of s sub p of n is actually 1 divided by p plus 1? And now, the fourth point here is actually quite interesting and something that I'd like you to explore on your own. Maybe find s sub p of n for a few higher values of p and see what happens in the second term of the expression. We have to exclude p equals 0 here for reasons I won't go into a lot of detail right now. But there is a very interesting pattern here for the second coefficient of s sub p of n that is something that you may find a bit curious the first time you see it. And finally, the big question. Is there a general formula for s sub p of n that only depends on p and n? That is, can we find a master formula that sort of puts all the formulas we have found so far to shame, where you just plug in the correct value of p that you're interested in, and then you have that formula for s of p of n ready to go? Now, this fifth question is actually far more difficult than the other four questions. So, I think it's conceivable for some people watching this video to actually sort of solve points 1 to 4. But completely resolving the question in point 5 is really difficult. And if you'd like to find the answers to these questions and many more, I suggest that you search for sums of integer powers. This problem of finding a formula for s of p of n is a really old problem. It's interested mathematicians for millennia, and it has a very rich and interesting history. At this point, I could probably end the video with a pretty clear conscience, but there are a few things I still want to discuss. And one of them is to give some additional methods to find the formula for s sub 2 of n. The reason for this is that the methods I showcased so far in the video have been a bit unusual, to say the least, and they may not be that easy to generalize. It's perfectly possible to do so, but it may not be the most straightforward thing in the world. So I will showcase two additional methods of coming to this formula which are a bit easier to generalize. And these are, first off, the standard method, which uses Pascal's triangle, and the second method is something I came up with myself using the choice function. And these methods are quite similar in spirit in that they are both easy to generalize, but they are very hard to come up with on your own, and that is actually the reason why I didn't want to showcase them earlier. But at this point, I think they're a nice bonus to include. So let's begin this section by talking about Pascal's triangle and give a very brief crash course on the topic. So this is a way to arrange numbers in a triangle so that each entry is the sum of its neighbors in the previous row. So we get the following structure where we begin at the top of the pyramid with the number 1. And in the next row we have two copies of the number 1. And this is because they both are the sum of their only neighbor in the previous row. Now, in the other rows, more interesting things happen. So on these sides we just have the numbers 1 because all of these only have one neighbor in the previous row. But these numbers in the middle of the triangle are a bit more interesting because now they have more neighbors in the previous row. So for instance, this number 2 is the sum of 1 and 1, its neighbors in the previous row. And this number 3, for instance, is 1 plus 2, so on. And we have 6 here is 3 plus 3. So we see how these numbers come about in the triangle. And we can even use this to generate a new row of the triangle, or as many rows as we'd like. So for instance, the next row becomes, first we have 1 here at the end, then 1 plus 4 equals 5, and then we have 4 plus 6 equals 10, and then 6 plus 4 is 10, then 4 plus 1 is 5, and then finally we have 1 at the end. And we can just continue this construction, add as many rows as we'd like. It's very quick, it's very easy to do once you get the hang of it. Now, this triangle has many interesting properties, but right now we shall only consider its connection to binomial expansions in particular. So, what is a binomial expansion and what does it have to do with Pascal's triangle? Well, a binomial is an expression of the form a plus b to the nth power, where a and b are just some arbitrary numbers and n is a natural number. Pascal's triangle can be used to quickly expand these expressions by hand. So we get the following table here, and we see that each row here is connected to one specific value of n. So here we have n equals 0, here we have n equals 1, and so on and so forth. Let us look what happens for different values of n here. So for instance, let us just begin by looking at this row n equals 0. Well, a plus b to the 0th power is just equal to 1. We see we have the number 1 corresponding to this in Pascal's triangle. And in the row here associated with n equals 1, what do we have? Well, a plus b to the first power is just a plus b, and we have corresponding to this two numbers in the triangle, 1 and 1. And what do these numbers 1 and 1 correspond to? Well, this number 1 is connected to the fact that we have 1 times a. And this one over here is connected to the fact that we have 1 times b. And in the row associated with n equals 2, we have the following expression here. So we see that a plus b squared is equal to a squared plus 2ab plus b squared. And we have associated to this three numbers in Pascal's triangle, 1, 2, and 1. So what are these connected to? Well, this 1 here is connected to the fact that we have 1 times a squared. Then 2, well, we have 2 times ab. And then finally, we have 1 times b squared in the expression. And this pattern continues for any row in the triangle associated with any power of a plus b when we expand it. So for instance, we have a plus b cubed becomes 1 times a cubed plus 3 times a squared b plus 3 times ab squared, and then finally plus 1 times b cubed. There is one thing we have to take note of in this expansion of a plus b to the nth power that is quite important, and that is the order of the terms that we have here. So first we begin with a to the highest possible power, so here it's a cubed, and then for each term we go to the right, the power of a in the term decreases by 1. And likewise, as the powers of a decrease in the expression, the powers of b will increase. So here we have b to the 0th power, then b to the 1st power, then b to the 2nd power, and then finally b cubed. So that's how we can compute a plus b to the nth power using Pascal's triangle in a very convenient way. And it is actually very practical to use, and it is much quicker than just computing a plus b to the nth power manually by hand. Now this can be used for many things, and in particular it can be used to see that k plus 1 cubed is just equal to k cubed plus 3k squared plus 3k plus 1, because 1 to any power is just equal to 1. And this in turn implies that k plus 1 cubed minus k cubed is just equal to this part over here, which we get from the expansion. So at this point you may say, okay, so what's the big deal? We just have a random expression, we have written it in a different way. What's the point of all this? What can we use this for? How is this related in any way to s sub 2 of n? Well, that's the thing. There is a bit more than meets the eye to this expression, and it all comes together once we consider the following sum s, which is the sum as k ranges from 1 to n of k plus 1 cubed minus k cubed. And using what we just saw, we can actually simplify this sum in the following way. So we get that s is actually equal to the sum as k ranges from 1 to n of 3k squared plus 3k plus 1. And this here can be split up into three separate sums. So we get that s is actually equal to 3 times s sub 2 of n plus 3 times s sub 1 of n plus s sub 0 of n. And of course we already know what s sub 1 of n and s sub 0 of n are. The reason why this is so useful is because we can actually compute s in a different way, and it has to do with the fact that it's a telescoping sum. So what do I actually mean by this? Well, that s is a telescoping sum simply means that many of its individual terms cancel out once the expression is expanded. So let me show you exactly what happens here. So s is equal to the sum as k ranges from 1 to n of k plus 1 to the 3rd power minus k to the 3rd power, and I can split this into two separate sums as follows. And what happens now when I write these sums out explicitly? Well, I get the following thing here, where we have, first off, in the top here, we have this sum over here, and then in the bottom, we have this sum over here. And what's interesting about what I just wrote out is that many terms just cancel out against one another. So for instance, we get 2 cubed cancelled by 2 cubed, 3 cubed cancelled by 3 cubed, and all the way up to n cubed, which is cancelled by n cubed. And all terms in between just cancel out. And what are we left with? We're left with only two terms, n plus 1 cubed and then minus 1. So we know that s is actually equal to n plus 1 cubed minus 1, and we have now a closed form expression for it. At this point, we all know what to do. We just use the fact that we have two alternative ways of writing down the same thing, and then we set these equal to one another. And from this, we simply isolate this term here. And what we end up with at the end of the day is the following expression, which we can expand and simplify using the formulas for s sub 1 of n and s sub 0 of n to give us a formula for s sub 2 of n from before. So this method is actually very interesting. We just look at some random expression and then suddenly, out of nowhere, s sub 2 of n is just conveniently hiding in there, and from that we can just extract our formula with no effort. And at this point you may feel like taking a break, but I don't think you need it, and I'm certainly not going to give it to you. Instead, I'm just going to show you the second additional method for computing s sub 2 of n that I came up with on my own. And it all comes down to the choice function. So what is the choice function exactly? Well, imagine that you have a box with 5 identical slots and that you have 3 identical balls. Now, assuming that one of the balls fits neatly into one of the slots, in how many ways can the 3 balls be arranged into the 5 slots? So in order to solve this problem, we usually think in the following way. First off, we have 5 possible placements for the first ball. So for instance, I can place the first ball here, or here, or here, or here, or here. Any of the 5 slots is available. And then, once the first ball has been placed, the next ball only has these 4 available slots left. And then finally, once the 2 first balls have been placed, say here and here, we see that the third ball only has 3 available slots left. So from this we get that there are exactly 5 times 4 times 3 possible ways to place the balls if we take their order of placement into account. So for instance, if we say that this placement is distinct from this placement, then we get 5 times 4 times 3 possible ways to place the balls. But this is actually not what we want. For instance, we want this arrangement to be identical to this arrangement, or this arrangement. It shouldn't matter which ball was placed first and which ball was placed last into the slots. And we need to be a bit careful here. So what we have, 5 times 4 times 3, leads us to overcounting, and we need to adjust for this. So let us consider the box once more. Given any arrangement of the 3 balls into the 5 slots, the placed balls can be permuted amongst one another. So for instance, if I have these 3 balls placed out, I can simply say that one of them is the first ball, and one of them is the second ball, and one of them is the third ball. So for instance, I can just claim that this ball is number 1, or I can claim that this ball is the first ball, or this ball is the first ball. So for the first ball, I will have 3 possible choices for my first ball. And once I have chosen my first ball, I will have 2 remaining candidates for my second ball. So I get that, say that this is the second ball. But now I only have 1 remaining candidate for the third ball. So in total we get 3 times 2 times 1 such permutations. And hence, since we don't care about the order of placement of the balls, we get that the number of ways to arrange 3 identical balls into 5 slots is what is known as 5 choose 3, written this way, which is by definition 5 times 4 times 3 divided by 3 times 2 times 1. So we have, first off, all the ways we can place the 3 balls, taking into account the order of placement, and then in the denominator we take into account the fact that in the numerator each arrangement is counted these many times. So this can be written also using factorial notation in the following way. And in this notation, what do we have? Well, we get that this expression up here is just equal to 5 factorial divided by 2 factorial, and then we have that the denominator here is just the 3 factorial here. So that's how these work and how these interplay with one another. So all of this can be generalized to any number of balls and any number of slots, and we get what's known as the choice function, written in the following way. And we say that this expression is called n choose k. And by definition, it's equal to n factorial divided by n minus k factorial times k factorial. And this can also be written in the following way. So it can be written as n times n minus 1 times and so on all the way down to n minus k plus 1, all divided by k times k minus 1 times k minus 2 and so on all the way down to 1. And here, just once again, we note that this part here corresponds to this numerator here. And then we have this k factorial corresponding to this denominator over here. And here again, we have that n denotes the number of available slots in our box, and k denotes the number of balls that are to be placed. So at this point you may ask, okay, so what are we doing here? Why are we looking at the choice function? Well, the point of it all is that we want to consider the following expression, n plus 2 choose 3, which is by definition equal to n plus 2 times n plus 1 times n, all divided by 3 times 2 times 1. Initially, this is quite similar to the previous method we looked at, where we just look at some random expression, where it's not really clear why we're looking at it. But I promise you, there is actually a method to the madness, and this comes up when we start looking at alternative ways of looking at this number. So we know what the numbers n plus 2 and 3 stand for in the expression n plus 2 choose 3. n plus 2 is the number of available slots, and 3 is the number of balls. So let us now draw this scenario out explicitly. We have the following situation. We have a box with first n slots marked in black, and then we have 2 additional slots marked in red, for reasons we shall see quite soon. Previously, when we placed the balls into the slots, we thought in terms of the first, the second, and the third ball to be placed. But in this case, we want to think in a different manner. We instead want to think about the leftmost, the middle, and the rightmost ball to be placed. So what difference does this actually make? Well, let us think about where the leftmost ball can be placed. The leftmost ball can of course be placed here, for instance, because we have now 2 available slots for the remaining 2 balls. But the leftmost ball cannot be placed into this slot here, because then we don't really have enough slots to the right of it to place the 2 remaining balls. So where does this lead us exactly? What does n plus 2 choose 3 become given this characterization? Well, we can compute it the following way. We can think of it as a sum where first we think how many ways can we place the remaining balls once the leftmost ball is maximally to the right. And then we take all of those possibilities and then we add the number of ways to place the 2 remaining balls once the leftmost ball is moved 1 step to the left. And then we continue this process all the way down to here and here. So we get the following expression at the end of the day, that n plus 2 choose 3 is equal to the sum as k ranges from 1 to n of k plus 1 choose 2. So here we think about k as the number of slots away from the red ones the leftmost ball is. So for instance, if the leftmost ball is right here, then it is just 1 slot away from the red ones. But if the leftmost ball is here instead, then it is 2 slots away from the red ones, and so on. And then we have that k plus 1 simply denotes the number of slots to the right of the leftmost ball. So for instance, if we place the leftmost ball here, which corresponds to k equals 1, then we see that we have 2 slots remaining to the right of it, where we can place the remaining 2 balls. And if the leftmost ball is here, then we have instead 1, 2, 3 slots to the right of it, where we can place the 2 remaining balls. Let us now expand upon what we just discovered. So on the one hand, we had that n plus 2 choose 3 is equal to n plus 2 times n plus 1 times n, all over 3 times 2 times 1. And on the other hand, we have that the same thing is equal to the sum as k ranges from 1 to n of k plus 1 choose 2. But this expression can of course be expanded and simplified, and what we end up with is that this is just equal to the following sum, since k plus 1 choose 2 is by definition k plus 1 times k divided by 2. And expanding this sum and splitting it up into 2 separate sums, we get that this will be equal to 1/2 times the sum as k ranges from 1 to n of k squared, plus 1/2 times the sum as k ranges from 1 to n of k. But these can be rewritten as s of 2 of n and s of 1 of n respectively, and we end up with the following situation. And now, for good measure, we can just use the formula for s of 1 of n to get this expression. And now we can see why this method will, at the end of the day, work. We have managed to find s sub 2 of n just hiding here within this expression in plain sight. And now all we have to do is to isolate it. Now, combining these two characterizations of n plus 2 choose 3, we can manipulate the expressions a bit, and finally we end up with s sub 2 of n being equal to this expression right here. And of course we can just simplify this a bit, and what we will find out is that it's the exact same expression for s sub 2 of n that we found before. Now, at this stage we have derived the formula for s sub 2 of n in more ways than anyone would ever need to. And even though I know that I've overstayed my welcome by quite a bit, there are a few more things I want to talk about. First off, some remarks on what we just saw. So these methods that I just showed are quite interesting, and I think they're also quite elegant. Moreover, they are more straightforward to generalize to sums of higher powers than the other methods we saw in this video. For instance, if you want to generalize the method using Pascal's triangle, you just need to go to a lower layer in the triangle, and if you want to generalize the method using the choice function, you just need to add more balls to place into the slots. But these methods are also a bit different from the ones we saw earlier in the video in that they are a lot more difficult to come up with on your own. Because, at some point in these solutions, you just look at some random expression and then from nowhere, the sum we're interested in just happens to hide there. But that is not at all obvious, so I want to talk a bit about how we can come up with this kind of solution strategy to a problem. Because this is not something I see many people discuss. Maybe because they don't know, maybe because they don't care. I really don't know, but I do want to talk about how we actually get to these weird solution strategies for difficult math problems. So the answer to this question of how we find these solutions is actually quite simple. We do it by not trying to solve the problem at all. And this is something I realized when I devised this method using the choice function. I didn't come up with this method by looking at the choice function and trying to make that work for solving the problem of finding a formula for s sub 2 of n. I had already seen the formula for s sub 2 of n, I had already derived it in many different ways at that point. But when I was working on the choice function in a completely unrelated context, I just got these weird numbers out of it, and I started mistrusting the standard definition that I had used in the past. And that's why I started looking at it from the beginning, with no presuppositions, and just worked out this alternative way of viewing the whole thing. And that's when I realized what was hiding inside. It was because I was just looking at what happened when I was playing around with the choice function, and then it just happened to be that I recognized s sub 2 of n hiding in there. So now I want to sort of round things off by talking about why this problem is so appealing to me and how I came into contact with it to begin with. So first off, this problem of finding the formula for s sub 2 of n is not an easy problem. In fact, most people are going to fail, and it's not even going to be close. But at the same time, the problem is not so extraordinarily difficult that people can't solve it when they're given some hints. And the fact of the matter is that I do think that, a talented high schooler could probably solve this, maybe even completely on their own. And, the problem is also very accessible in the sense that you don't really need a lot of mathematical knowledge to understand what the problem is. And that's one of the reasons why it actually does have a very rich and interesting history. I just love reading on even Wikipedia just about the different aspects of the problem and its generalizations that people sort of worked on over the centuries and what they came up with. They came up with some pretty interesting stuff, and it's so fun to read about. And moreover, as an educator, this problem gives me a lot of chances to showcase different tools and techniques mathematicians use when faced with a difficult problem. For instance, I can showcase how we sort of get unstuck by not viewing the main problem directly, but rather by trying to modify it into a simpler version of itself, and then sort of get some ideas to get unstuck when we really have no idea what we're gonna do.
And moreover, it gives me the option of really talking about how sometimes when we solve a problem, there can still be a lot left to learn and understand even after we have solved it in one way. Because when we talk about, say, s sub 2 of n, why are there so many different ways of finding a solution to the problem? I do find that so interesting. And, the skill of delving deeper into something even after you have sort of solved the problem once, it's something that I do find is sort of an underrated skill for most people. And here I think you can gain a lot of appreciation for that kind of process by just seeing how much you can uncover by looking at this problem again and again and again from different angles. So, with all this said, I do find that this problem is sort of almost the perfect example of what you want a problem to be from a pedagogical perspective. And working with it has given me so many ideas for my own teaching moving forward. And essentially, this video is actually a first draft adolescent plan, because when I came into contact with this problem, it was when I was sort of being a teaching assistant for a specific course for undergrads in computer science. And the lesson went something like this. I began by briefly talking about sums of integer powers, and I noted how we had previously seen how to compute s sub 0 of n and s sub 1 of n. And then the students were tasked with finding a formula for s sub 2 of n, and the plan, or the structure that I had been given by the one in charge of the whole course, was to give the students a sequence of step-by-step instructions to derive the formula for s sub 2 of n using Pascal's method. And I understand why the lesson was structured the way it was from the examiner, and if anyone is interested, I can talk a bit about that in the comments. But for me, it felt like many students were a bit confused about what was going on during the lesson, and they weren't really given that sense of accomplishment of being able to find a method of doing this in their own way. And I think this is sort of something that was a lost opportunity, because I do think that with the right kind of hints and guidance, many people can come up with a pretty decent way of attacking the problem. And most methods they come up with can probably be modified in some way to actually solve the problem. So this is something I set out to do in this video, to try and find sort of a way of improving this lesson to give people the opportunity to find their own way through this kind of problem, and in that way be more engaged and understand why they do a certain step in their solution, and not just feel like all the steps here we do are given to us from some weirdo in the background and we have no idea why we're doing it, and then somehow it just works out in the end. I want people to feel in charge of their own solutions. I really do want that, because I do think that's actually very important. And with all this being said, I think you know what I'm going to say now, that if you have any feedback to give, it would be greatly appreciated. If you have anything to add about your experience during this video, if you found some of the points I mentioned interesting, if you felt it got a bit too tedious when I brought up method after method of solving the problem, there are so many things you could say as a viewer that, from my perspective, are very difficult to appreciate for myself. And if you have anything to add, I would love to read it so much, So with all this being said now, I promise you this is the end of the video. Thank you so much for watching, and I hope it's been worth your while.